let us look at this application of Ampere's circuital law, which is to calculate the magnetic field intensity at a point inside a solenoid. Now, what is a solenoid? That's the first question, of course. A solenoid is a cylindrical coil of wire which acts as a magnet. So we have this solenoid here, and current I0 is flowing through this wire, which means current I0 is flowing through each turn of the solenoid. Another thing, if someone looks from this side, this end, he or she will see current flowing in the anti-clockwise sense. So therefore, this side of the solenoid acts as the north pole. So this side acts as the north pole, and if someone sees from this end, he or she will see current flowing in the clockwise sense. So therefore, this end acts as the south pole. So this is the south pole, this is the north pole. So therefore, this solenoid also acts as a magnetic dipole. Any magnetic dipole will have its magnetic field, don't forget, and the direction of the magnetic field inside the solenoid is from the south pole to the north pole, in this direction. So let I0 be the current flowing through the wire, or the current flowing through each turn of the solenoid, and n, small n, be the number of turns per unit length of the solenoid. Now, in order to calculate the magnetic field at a point inside the solenoid, using Ampere's circuital law, what we need to do is we need to consider a loop. Say, for example, we want to find the magnetic field intensity at this particular point, and that particular point is P. So what we need to do is we need to consider a closed loop, and this closed loop has to pass through this point. So in that sense, Ampere's circuital law is very similar to your Gauss's theorem in electrostatics, don't forget. So in electrostatics, while using Gauss's theorem, we used to consider a Gaussian surface. And this Gaussian surface had to pass through the point where we were required to calculate the electric field intensity. So likewise, while using Ampere's circuital law, at whichever point we want to calculate the magnetic field intensity, we have to have a closed loop. Not a surface in this case, but a closed loop. And the closed loop we consider is this rectangular loop A, B, C, D. As you can see, the rectangular loop is passing through the point where we are required to calculate our magnetic field intensity. Also, let us suppose that the length AB or CD of the rectangular loop is Y, and the breadth BC or AD is equal to L. And that is exactly what I've written over here. Therefore, applying Ampere's circuital rule to this loop ABCD, we get line integration of the magnetic field is equal to mu naught into I. Mind you, Ampere's circuital law tells us that the line integral of the magnetic field has to be equal to mu naught times the total current enclosed by the loop. So this current I is not the same as the current flowing through every single turn of the solenoid, which we are saying is I0. Now we are saying the length of AD or DA is equal to L. Furthermore, n is the number of turns per unit length. So, if n be the number of turns in unit length, then the number of turns in the length L, that is the number of turns in this length, will be n into L. Also, I0 being the current flowing through each turn, then the current flowing through NL number of turns will be NL into I0. Therefore, the current I enclosed by this loop ABCD is given by I, which is equal to NL into I0. Therefore, if this is equation 1, then substituting this value of I, we get integration B dot dl is equal to mu naught NL I0. Now look at this equation carefully. The left hand side especially, what we are doing is we are integrating over a closed loop. The closed loop is ABCD. So we are integrating over the closed loop ABCD. But since this closed loop is rectangular, what we can do is we can break this closed loop into 4 parts. That is, AB is one part, BC is the other part, CD is the third part, and DA is the fourth part. So what we are doing is we are breaking this left hand side into 4 parts, because of which we get this. So integration over AB of the magnetic field plus integration over BC plus integration over CD plus integration over DA. And mind you, the integration doesn't have a ring now, because we are not integrating over a closed surface. So we've broken the closed loop ABCD into 4 parts, 4 sections. We are integrating the magnetic field over AB first, then over BC, then over CD, then over DA. And this whole thing, the sum of these 4 different parts is equal to mu naught N L I naught. This is our equation 2. Now what we get from this equation 2 is that the integration of the magnetic field over AB is equal to the integration of the magnetic field over CD, and these two things are equal to 0. So to say, the first term and the third term, they are both equal to 0, because the angle theta between B and DL is 90 degrees. So this is going to give us B DL cos theta, of course. Now if theta is 90 degrees, then cos of 90 degrees being 0, so both of these two terms becomes 0. Let us also check that in the picture. So we are saying integration over AB and integration over CD, it's 0, because we are trying to find the magnetic field inside the solenoid, and inside the solenoid we've seen already that the direction of the magnetic field is from the south pole to the north pole, which is along this direction, which is along the axis of the solenoid, so to say. And DL, what is DL? When we consider the first term over here, DL is a small elemental length over AB, and when we consider the third term CD, then DL is a small length over here. So this DL and this DL, they are both perpendicular to the direction of the magnetic field, you can see. So therefore theta is 90 degrees, because of which the first term and the third term, both of them become equal to 0. Also we'll see that the second term in equation 2 also becomes 0. That is because the second term says we're integrating the magnetic field over BC. So BC is over here. Now this BC being far from the inside part of the solenoid, what happens is outside the solenoid the magnetic field is very weak. So to say, B itself, when we are integrating over BC, becomes 0. So therefore the second term also becomes 0. So what we are only left with is the fourth term in equation 2. Now the fourth term itself is equal to mu naught N L I naught. So integration of B over dA is equal to mu naught N L I naught. Now we are integrating the magnetic field over dA. So when we consider a small elemental length along dA, you can see that the direction of the elemental length and the magnetic field is the same. That is, the angle theta between the magnetic field and the elemental length when we integrate over dA is 0. Therefore, this equation can be written as B dl cos of 0 degrees, which is mu naught N L I naught. The right hand side is the same. So integration over dA becomes this much. And finally, B comes out to the integration because inside the solenoid at all points the magnetic field is a constant. So therefore B comes out of the integration, and we are only integrating over dl. So this becomes mu naught NL I naught. Now the integration of dl along this line dA is simply equal to L, because when we integrate small dls along this line, we are finally going to get the length AD or dA, which is L. So therefore integration of dl over dA is going to give us L. So B into L becomes this much. Now L, they divide each other, because of which we get the magnetic field inside the solenoid to be mu naught N I naught. So we see that the magnetic field inside a solenoid is dependent only on the number of turns of the solenoid and the current flowing through the solenoid. The magnetic field inside the solenoid can be increased, and also it can be increased by increasing the strength of the current flowing through it.